On May 27, 1937, 200,000 people walked across a bridge that most engineers said could never be built. They walked in fog so thick they could barely see the towers above them. They walked over water so violent it had killed 11 of the men who built it. And they walked on a road deck suspended from cables containing 27,572 individual steel wires, spun by hand, strand by strand, across a strait where Pacific currents run faster than most rivers on Earth. The Golden Gate Bridge was not just an engineering project. It was a bet placed during the worst economic collapse in American history, financed not by the federal government, but by local citizens who put their own farms and homes up as collateral for the bonds. It was designed by a man most of the engineering establishment dismissed, built by workers who were so grateful for jobs during the Great Depression that taxi drivers and farmers showed up to the Union Hall claiming they had been iron workers their whole lives. And protected by a safety net so radical that 19 men who fell from the bridge and survived formed a club. They called it the Halfway to Hell Club, because when a bridge worker fell to his death, the others said he had gone to hell. The net only got you halfway there. This is the story of how they built it, not just what it looks like, but how every piece of it was placed, bolted, riveted, and hung over the deadliest stretch of water on the California coast. Before we go up, drop a comment and tell us where you are watching from right now and what time it is there. We want to see how far this bridge reaches. If you enjoy engineering deep dives that go beyond what you learned in school, take 1 second to subscribe. It costs nothing, and it tells us these stories are worth telling. To understand why the Golden Gate Bridge was so difficult to build, you have to understand the place. The Golden Gate is not a gentle bay. It is a narrow throat, barely 2 kilometers wide, connecting the entire San Francisco Bay to the open Pacific Ocean. Every 6 hours, the tide changes, and billions of cubic meters of ocean water surge in or drain out through this single opening. The currents can exceed 11 kilometers per hour. The water is more than 100 meters deep in places. The fog rolls in without warning, reducing visibility to almost nothing, and the wind blows hard enough to push a man off a steel beam. The idea of bridging this strait was first suggested in 1872 by a railroad tycoon named Charles Crocker. Most people laughed. Nearly 5 decades later, in 1919, city officials asked engineers across the country to estimate what it would cost. Most said over $100 million. Some said it was simply impossible. The currents were too fast. The water was too deep. The distance was too great. One engineer disagreed. Joseph Strauss, a man who had built hundreds of small drawbridges, submitted a proposal to build the Golden Gate Bridge for $35 million. The engineering establishment did not take him seriously. He was not a suspension bridge specialist. But Strauss had something the others did not. He would not stop. It took him more than a decade of political fights, lawsuits, and public campaigns, but in 1930, voters approved a $35 million bond measure to fund the bridge. The money would come not from Washington, not from the state of California, but from the citizens themselves. Local residents put up their farms, businesses, and homes as collateral. If the bridge failed, they lost everything. Construction began on January 5, 1933, in the teeth of the Great Depression. The first problem was the most basic one. Where do you put the towers? A suspension bridge works by hanging the road deck from cables, and the cables hang from towers. The taller the towers, the more efficiently the cables carry the load. Strauss calculated the optimal tower height at 746 feet, 227 meters above the water. Each tower would contain 44,000 tons of steel and 600,000 rivets. But before anyone could worry about the towers, they had to solve the question that nearly killed the project before it started. How do you build a foundation for the South Tower?
In open ocean, over 1,000 feet from shore, in water 100 feet deep, with currents that could sweep a diver away in seconds. The North Tower was relatively easy. It sat close to the Marin County shore, where the bedrock was near the surface and the water was calmer. A standard cofferdam handled the job, but the South Tower was a different story entirely. It had to stand in the open Pacific, fully exposed to the tidal surge of the entire bay. What they built to solve this problem was unlike anything attempted before, and the ocean fought them every step of the way. First, workers built a temporary timber trestle from the San Francisco shoreline out to the tower site. It was the only way to get workers and materials to the location. In 1933, a freighter collided with the trestle and destroyed a section of it. 2 months later, a storm wiped out more than half of the rebuilt structure. They repaired it again and kept going. Divers descended up to 110 feet into the strait to prepare the foundation. They worked in near total darkness, in water so cold and so fast that they could only operate during the brief windows when the tide changed and the current slowed. 4 times a day, for as little as 75 minutes each time. That was it. That was the window. In those windows, the divers placed dynamite charges on the seafloor. The blasts broke through rock and sediment to expose the bedrock beneath. High-pressure hoses cleared the loosened material. Then the divers guided massive steel forms and concrete funnels into position on the cleaned bedrock, working by feel as much as by sight in the murky water. What they were building was the fender, a massive oval-shaped concrete wall, bigger than a football field, that would enclose the entire tower site and protect it from waves and currents. Think of it as a bathtub built in the middle of the Pacific Ocean. Once the fender walls were complete, the water inside was pumped out, and workers could build the tower foundation in the dry, inside a concrete fortress that held back the full force of the strait. The fender walls were 12 meters thick, and here is a detail that shows how clever Strauss was. After the foundation was complete, the space inside the fender walls was flooded again, deliberately. The weight of the water inside the walls made the entire structure heavier and more stable against the currents. The ocean that had tried to destroy the construction site was now being used to hold it in place. With the foundation set, the towers went up, and they went up fast. Each tower is made of 2 legs, 27 meters apart, connected by horizontal beams called struts. The legs are not solid steel. They are built from hollow cells, individual steel boxes riveted together one on top of another like enormous building blocks. Strauss designed this cellular structure to be both lighter and stronger than solid steel, and it allowed workers to climb inside the towers during construction, riveting from the inside out. The steel sections were prefabricated off-site and brought to the bridge by ship. Derricks, tall cranes mounted on the towers themselves, lifted each piece into position. Workers stood on scaffolding hundreds of feet above the water, in wind and fog, driving 600,000 rivets by hand. A rivet crew worked in teams of 4. One man heated the rivet in a portable forge until it glowed, tossed it to a catcher who placed it in the hole, while a third man held a heavy steel bar called a dolly against the back, and the fourth drove the rivet home with a pneumatic hammer. 600,000 times. They were paid between $4 and $11 a day. During the Depression, that was a fortune. Men lied about their experience to get the work. Taxi drivers said they were iron workers. Farmers said they had been climbing steel their whole lives. The union knew. They hired them anyway. There was a bridge to build, and the men were willing to risk their lives to do it. And lives were at risk every single day, because at this height, in this wind, on wet steel slicked by fog, a fall meant death. In the 1930s, there was an unwritten rule in heavy construction: 1 death for every $1 million spent. On a $35 million project, that meant 35 men were expected to die. The industry accepted this. Joseph Strauss did not. He did something that no major construction project in America had ever done before. He spent $130,000, an enormous sum during the Depression, on a safety net. It hung beneath the entire length of the bridge deck, extending 3 meters wider on each side and 5 meters beyond each end. It looked like a circus net. Workers mocked it at first. Then it started catching them. Between 1936 and 1937, 19 men fell from the bridge. Every one of them hit the net and lived. They formed a club in the hospital ward at St. Luke's, where 4 of them were recovering from injuries at the same time. An iron worker named Al Zampa explained the name. When a bridge worker fell to his death, the others said he had gone to hell. The men who hit the net had only fallen halfway. They called themselves the Halfway to Hell Club. Zampa later said the net changed everything. Workers moved faster. They took the risks that speed demanded, because they knew that if they slipped on a wet beam, the net was there. Strauss had not just saved lives, he had made the bridge faster to build. But the net could not save everyone.
On February 17, 1937, just 3 months before the bridge was finished, a crew of 12 men was working on a temporary scaffold beneath the deck, stripping formwork. At 9:20 in the morning, the scaffold broke. 5 tons of steel and timber fell away from the bridge. It hit the safety net, and for the first time, the net failed. The weight of the platform tore through it, and 12 men fell 220 feet into the Pacific. 2 survived. 10 did not. In a single morning, the project's death toll went from 1 to 11. Those 10 men, plus 1 who had been killed months earlier when a beam fell on him, became the final count. 11 dead on a project that the industry expected to kill 35. Strauss had proven that a safety net works. He had also proven that no net can catch everything. With the towers complete and standing 746 feet above the water, it was time for the most visually spectacular phase of construction: the cables. You might assume the main cables are single solid ropes. They are not. Each of the 2 main cables is over 90 centimeters in diameter and contains 27,572 individual wires. The total length of wire used in both cables is over 129,000 kilometers, enough to wrap around the Earth more than 3 times. The cables were not manufactured in a factory and shipped to the site. They were spun in place, wire by wire, across the strait. Here is how. First, workers built temporary catwalks, narrow walkways of wire and wood that hung from the tower tops and sagged down to the anchorages on each shore. These catwalks were the only way to access the cable during spinning, and walking on them in the wind was an act of faith. Then, the spinning began. A system of wheels carried individual wires back and forth across the strait, each wire draped over cable saddles at the top of each tower. One by one, the wires accumulated. Workers on the catwalks gathered them into bundles called strands, clamped them together, and pressed them tight using hydraulic compactors. Then the strands were wrapped in galvanized steel wire, sealing them into the round cross-section you see today. From the ground, the finished cable looks like a single pipe. It is not. It is 27,000 individual wires, clamped, compressed, and wrapped so tightly that they act as one. The engineering behind this is why a suspension cable can flex in the wind without snapping. Each wire shares the load, and if one breaks, the others absorb the difference. With the cables in place, the deck could be hung. 250 pairs of vertical suspender cables were attached to the main cables, and from them, the steel truss structure of the road deck was assembled, section by section, working outward from each tower toward the center of the span. Here is where balance mattered. Workers had to assemble the deck symmetrically, adding equal weight to both sides of each tower at the same time. If one side got too heavy before the other caught up, the entire cable system would shift, the tower would bend, and the geometry of the bridge would be compromised. The truss sections were prefabricated and brought to the site by barge. Derricks lifted them into position, and riveting crews connected them to the suspender cables. Then came the concrete road deck itself, poured on top of the steel structure using wooden formwork with steel reinforcing bars welded to the structure below. To handle thermal expansion, the bridge deck expands and contracts with temperature. Strauss divided the road into 7 separate sections connected by finger expansion joints. On a hot day, the gaps close by nearly 10 centimeters. On a cold night, they open. The bridge breathes. And then one more detail that Strauss chose, one that had nothing to do with engineering, but everything to do with why this bridge became the most recognizable structure in America: the color. The steel arrived from the factory coated in a standard red lead primer. Most bridges were painted gray or silver, but the consulting architect, Irving Morrow, looked at the red primer against the fog and the ocean and the golden hills and said, "Keep it." He developed a custom shade called International Orange. It was warm enough to stand out against the gray fog, bold enough to complement the natural landscape, and visible enough from any distance to declare that this bridge was not trying to blend in. It was announcing itself. The Golden Gate Bridge opened to pedestrian traffic on May 27, 1937. 200,000 people walked across it that day. Vehicle traffic began the next day. The bridge that most engineers said was impossible financed by citizens who risked their own homes, designed by a man the establishment dismissed, built by workers who lied about their qualifications to get the job, and protected by a safety net that started a revolution in construction safety, was open. Total construction time, 4 years, 4 months, and 22 days. Total cost, $35 million. Not a dollar of federal money. But the story has one more chapter. On the bridge's 50th anniversary in 1987, the city invited the public to walk across it again. 300,000 people showed up, and as the crowd packed the deck from tower to tower, something happened that no one had predicted. The bridge sagged. The combined weight of 300,000 human bodies pushed the road deck down by nearly 2 meters. The towers bent inward, the cables stretched. Engineers watching from the shore held their breath. It was the heaviest load the Golden Gate Bridge had ever carried, far heavier than any traffic scenario Strauss had designed for. The bridge held. The cables absorbed the load. The towers flexed and returned to position. The structure that Joseph Strauss designed in the 1930s, with slide rules and hand calculations, had just passed a stress test that no computer model of that era could have predicted. 89 years of wind, 89 years of fog, 89 years of salt water, earthquakes, and traffic. And the bridge still stands exactly where those 11 men died putting it. The next time you see it through the fog, look at the towers. Each one contains 600,000 rivets driven by hand by men who earned $4 a day and considered themselves lucky. Look at the cables. 27,000 wires spun one at a time across a strait that tried to kill everyone who touched it. And if you look down, you will not see the net. It was taken down after the bridge was finished, but somewhere beneath that deck, the ghost of it is still there. The idea that started a revolution, that a worker's life is worth more than a schedule. Every megastructure we decode on this channel starts with a question from you. What should we take apart next? Drop it in the comments. Hit subscribe. Turn on notifications. The next structure goes even deeper.